Let me wait for another 5 minutes and till 4 5, and then we'll start. So when while we are waiting, let's discuss some of the things that were discussed in the week 12 sessions, and I'm not going to cover all of those things because it's just monotonous, right? We have covered genetic algorithm, particle optimization, particle swarm optimization, all these things in R. So it's just a matter of changing the syntax and putting it into MATLAB. So we need not waste our time on that. What we will do is we'll discuss the concepts involved in multi-objective optimization as far as I have understood from the shared videos. And we'll see these five methods that were discussed, and then we'll solve one problem uh, by non-dominant sorting genetic algorithm NSGA2 in R, and the same problem we will solve in MATLAB using the multi-objective genetic algorithm MOGA. Yeah, so you may might have noticed that my I'm not feeling well that much today, so we'll see. We'll not go beyond 1 hour, but if you have some doubts, then maybe I can stick around. Otherwise, as soon as we finish the things that I have discussed, that I will be showing, then I'll end the session. Sorry for the trouble. Okay, 3 more minutes. Or should we wait 3 more minutes? Well, I don't think anyone's gonna join, so better to start. Okay, multi-objective optimization. What do we mean by multi-objective optimization? So in class, sir described one of the points, that was that the optimization nature for the two objective problems is different. So you might be thinking that, okay, if one is maximize, another is minimize, maybe we can use multi-objective, we have to use multi-objective, but that's not the case. We have to study the objective functions. So we have our so let me show you. So let's say we have two variable function f, and we have two optimization functions, two functions that need to be optimized. That is f1, that is a function of x1 and x2, and f2, that is a function of x1 and x2. Now, to know whether we need actually a multi-objective function, what you do is you choose a random space of x1 and x2 between the search domain that we have discussed, like x1 lower limit, x1 upper limit, and x2 lower limit, x2 upper limit. You generate some random points, you calculate the value of f1, f2, then you plot it. Let's say we have f1 on the y-axis, f2 on the x-axis. When you plot it, and the relation that you get between or the line that you get, the collection of points that you get in f1 and f2, it looks something like this, means or something like this, or something like this, kind of trying to say that f1 is proportional to f2 power something, and it can also be f1 proportional to f2 power something plus constant. So in that case it will be this kind of thing. So in this case, what you can observe is that when your f1 is increasing, your f2 is also increasing. So let's say if you have a problem that requires, so it's kind of a proportional relation between f1 and f2. Okay, so we have a proportional relation between f1 and f2. Then we cannot, directly proportional I should say, we cannot or should not use multi-objective. We can do the same thing with single objective also. Let's say if this is the case that you have, and here you can write a also constant. It can be negative, this constant that is multiplied with the f1 f2 power n. It can be negative, it can be positive. In that case you just have to multiply minus sign to the objective to bring them to the same nature. Okay, so now that we know when to use multi-objective functions, what we will do is let's discuss the methods that were discussed that will be used for solving the multi-objective optimization problem. So first one is, it is called vector evaluated genetic algorithm. So how did sir express this? So how it was written was, you have a set of, let's say this is a generation or initial solution, and you have set of solutions x1 x2 till xn. So this is has n solutions, and each solution will have some small x and small x1, small x2, like that. Okay, and you have, let's say, n. So this is n number of solutions in one generation. Let's say you have k objective functions. Then you'll have f1, f2, and fk. What vector evaluated genetic algorithm asks us to do is, you divide this n group of n solutions in a generation into k groups. That's up to you how you divide. It can be equally divided. You divide it into k group and use, let's say this is the first group x1 and x2. You use this for optimizing f1. So let's say if you were to maximize f1, f2, fk, so this is a maximization problem. Then you f1 x2 you use for f1, and some x r and xr plus 1 you use for fr, something like that. So what will happen in this case? So if you remember, let's discuss, let's see only one objective problem. When, let's say this is the f1, and when we did the optimization maximization, we saw that the points were kind of centered around these things. The points were kind of centered around the optima, you know. So what you will get after you do this vector evaluated genetic algorithm is, you will get, let's say we have three dimensions. Let's say k is 3, and f1 and f2 and f3. Then you will have a point here on the f1, you will have a point on the f2, you will have a point on the f3. Maybe not exactly on the f1, f2, f3, but approaching towards f1, f2, and f3. And this is not what we want. So one more thing, whenever we are trying to optimize multi-objective functions, we let's say, and we are not given how much priority or how much weightage we have to give to a certain objective function. Then what we do is, we create a plane, a surface, a line, whatever it is, based on the number of dimensions or the number of objective functions. that is going to have different proportions of f1, f2, and f3. So it will kind of create a 3D surface. In this case, it should create a 3D surface, and we should be able to choose any point in this 3D surface based on our requirement, and that would be the solution for multi-objective optimization. Okay. Okay, so but that's not what we are getting in the vector evaluated genetic algorithm. So that's one of the drawback of vector evaluated genetic algorithm. Now let's discuss about the another one, that is non-dominated selection heuristic. So I got confused when I was going through the video, you know. So here, sir discusses about the Pareto optimal front, and it's nothing but the plane that I talked about, which is consists of different weightage of the optimization functions. So we want a Pareto optimal front. To get that, what we need to do? Let's consider two objective function f1, f2, and let's say we have two variables also, x1, x2, and they are something like this. They are randomly oriented in the domain in which we are going to do the optimization. So what we do is we perform this optimization, and then we get the value of some f1, some f2, and we plot it. So let's plot it here. We plot, it will be something like this, and this line, the outermost line, is called our Pareto optimal front. So there will be no point that is coming here. The last line of this objective function space, or let's say the starting line, is called the Pareto optimal front. Let's say, and you have a maximization problem. Okay. So how do you do this? Let's say in one generation you had n solutions, or let me be consistent with what sir was using. Let's say we had capital N solution in one generation, and out of those capital N solutions, there are n solution that are non-dominated, n solution that are non-dominated. So if I want to keep this here, so I think I did a mistake. It should be minimization problem. Yeah. So it's a minimization problem, and the n is the non-dominated solution. So what to do? What does that mean is there are n points on this particular Pareto optimal front. Okay. And there are n minus n points that are dominated. We will see what does it mean by dominated and non-dominated. It's a very useful concept, and you can get easily confused in this particular concept. Okay, so n minus n is the non-dominated solution. What we do is we subtract epsilon, that is a pre-decided value, from all the fitness values of this non-Pareto front points or dominated points, one by one. And how much we have reduced? We have reduced n minus n into e, sorry, epsilon. And then we distribute this equally into the non-dominated solutions. So how do we distribute equally? So we just divide by the number of non-dominated solution, and this will be added to each fitness function of the non-dominated solution. So when we do this, so what we are doing is we are artificially increasing the chances of the points that are on the Pareto optimal front to get selected, and in that case we will, in the final solution, we will have some front which is the Pareto optimal front, and that's what the solution we want. Okay, so that's it with the non-dominated selection heuristic. Okay, and let's discuss about now about the third one, that is weighted based genetic algorithm. Hmm. So if you remember your vector evaluation genetic algorithm, you saw that if you had f1 and f2, let's take f1 and f2, then you will get some points here, some points here, but all these things are missing in your Pareto optimal front. So what we can do to get to fill these points is, we can see, look at this point, and let's say, and what we did, we gave all the solution to f1 here. So we divided x1, x2, the solutions in your generation, into two groups, and we gave group 1 to f1 and group 2 to f2, and we got some points here and some points here. So what we did, we gave the weightage of f1 here 1, and weightage of f2 here 0, and in this case we gave a weightage of f1 as 0 and weightage of f2 as 1. So what if we give some intermediate values of the weightage in the to f1 and f2, and see what we get. So what will happen is, let's say you have a group or vector of weightages, that is wait for function optimization function 1, and w2 the wait for optimization function 2. So what if you have 1 0 0.1 and 0, sorry, 0.9 0.1, and like that, you 0.8 0.2, you go to 0 and 1. So in that case, when you do this, what you will observe is, you will start seeing some points on the Pareto optimal front. So let's say if you have 10 groups of your weightage vector, then you will have 10 groups here. And so that we have like a widespread values in this Pareto optimal front, we have to do what is called niching, uh, redistribution according to the spacing. So that's done based on the distances of the solutions, that is x, from the objective function space. So because we want the spread to be in the objective function search space, and it was mentioned very clearly in the lectures that if you have some solutions, let's say x1 and x2 and x1 dash and x2 dash, these are the two solutions, and they are very close to each other. It is not necessary that the value of f1 f2 and f1 dash f2 dash also follows the same thing. It can happen that x1 is x1 x2, first point is here, second point is here, whereas when you go to the objective function space and f1 f2, you will see that they are far apart. So to get the spread of your on the Pareto optimal front, you need to calculate the distance between the function objective function space. So sorry. Okay, so and then you calculate the distance, you calculate Sij, and then you perform the niching, and then you get the modified fitness value, so that you can have a wide spread of solutions in the Pareto optimal front. Okay, so this was about weightage based genetic algorithm. The fourth one we have is MOGA. Quite a funny name, I thought, and its full form is multi objective genetic algorithm, MOGA. Okay, so what do we do in this thing? So in this, the selection is done based on the ranking of the uh, solution in the objective function space. Okay, and in the same way, niching is also done here to get the Pareto optimal friend. Oh, let's see. Let's understand how do we get the ranking. So selection is done based on ranking, and ranking is defined as 1 plus the number of ranking of I is defined as the 1 plus number of solutions that have dominated. Let me write it more clearly. Ni is the number of solutions that dominated the given solution. Okay, so let's see. We'll see the example that sir discussed in the class, and I feel that there was a slight mistake. Everyone makes mistakes, so there was a mistake that I noticed that I will be discussing here. Let's say you have mm, 4 5 points. Let me just randomly draw them. Sorry. 1 2 3 4 5 6 7 8 and 9. So let's say we have 9 points. Okay, or let's make this less crowded and yeah, this is fine. Let's say we have these many points. That is 7 points, I think, or we have 6 points. No, 7 points. So let's go to the values here. So here I am actually showing you how to identify the number of solutions that dominate a given solution in the objective function space. So what is the definition? Let's look at the definition once. A solution, oh sorry, a solution dominates another solution if and only if there is no. So let me take two solutions. Let's say a solution X dominates solution Y if there is no objective function of X worse than Y, and at least one objective of X is better than Y. So this kind of question can come into the exam. So be very clear about this. So you see here we have let's name these solutions. 1 2 3 4 5 6 and 7. Let's look at the solution 1 and 2 and consider that this is minimization. This is of also minimization of f2. Now you look at the solution 1. You see that f2, the solution number 2 here, it is better than the solution number 1 in terms of f1, but f so solution 1 is better than solution 2 in terms of, sorry, in terms of f2. So then these solutions do not dominate each other. They will have the same rank. What we can do here is let's get the rank of 1. Sorry, let's get the rank of 1, 2, 5, 6, and 7. So to get the rank of 1, we have to compare the domination and non-domination of 1 with 2, 3, 4, 5, 6, 7. So let's do that. Now coming to 1 compared to 2. We saw that 2 does not dominate 1. What about 3? Does it dominate 1? So here the answer is no, because in case of F1, 3 is better than 1. In case of F2, 1 is better than 3. Does 4 dominate solution 1? No. Does 5 dominate? No. And so on and so forth. So none of the solutions dominate solution 1. So it will have n is equal to 0. What about 2? So we see that again in case of objective function 2, solution 2 is worse than solution 1, but in case of objective function 1 f1, solution 2 is better than solution number 1. So 1 does not dominate solution 2. What do we mean by dominate actually? Let me take a second to explain that. Dominate means one solution is performing better or performing more what was expected of it than the other solution. So we have a minimization. So if the value of f1 is lesser than in solution 2, then we say that solution 2 is performing better than solution 1 in case of objective function 1. So solution 2 dominates solution 1 in case of objective function 1, and vice versa for objective function 2 in this case. Okay, what about solution 3? Does solution 3 dominate solution 2? So let's see. Solution 3 is the solution 2 dominates the solution 3 when it comes to f2, and solution 3 dominates the solution 2 and when it comes to f1. So this is also non-dominant. Same thing for the solution 4 also, and same thing for solution 5, 6 and 7. So this also has n is equal to 0. What about solution 3? Now you see, uh, in case of f1, solution 3 is performing better than solution 1 and solution 2, and in case of f2, solution 1 and 2 are performing better than solution 3. So they are not dominating solution 3. Solution 4, however, if you look at it, solution 4 is performing same as solution 3 in case of f2, but solution 4 is performing better in case of f1 because f1 is lesser for solution 1. So there is 1. So we have solution 4 dominating solution uh, 3. So let's write 4 here. And same way, solution 5, it actually performs better in both the cases, both in f1 and f2 than the solution 3. So this also will dominate the solution 3. What about 6 and 7? They are again similar to 2 and 1. They do not dominate solution 3. So what is our n? N is 2. And what will be the rank? Let me write rank also. Rank 1, rank 1, rank 3. Okay. What about 4? So in the same way, I do not want to spend more time on this thing. Let's do one more. Okay, let's do one more. Let's do for 5. So what you can do is you can check. Then you will see that none of the solutions dominate solution 5, and so n is equal to 0 and r is equal to 1. And what about solution 6? Solution 6 is also not dominated by anyone. N equal to 0, r is equal to 1, and but solution 7 is dominated by solution 6, and so that one will have rank of 2. So like this you can actually go ahead and check. uh, this is a very crucial concept when you are actually going to code manually this multi-objective genetic algorithm or nsga2. Okay, so uh, now that we have the ranking, we select the the selection function is based on ranking as I have written above, and we also perform here niching, and that is done between the solutions of same rank. Okay, again the formula or whatever the formula is shown in the ppt, that is applied on the solution in the objective function space, that is f1 and f2. Now that that is clear, let's go to the fifth and last method, that is nsga2. What is that? Non dominated sorting genetic algorithm. Okay. Hmm. So here also, so this is actually one should remember that this is an elitist. I don't know if I'm writing the spelling correct or not, but it is an elitist approach of getting the Pareto optimal front. Why it is called elitist? Because what we do is we have our population, we create our new generation, and this will let's call this an pi plus 1 and pi, and this will have n elements, this will have n elements. When we create this to perform the selection, the solution pool will include both the population, initial population or the past population, and the new generation. And since it is called sorting, you must have understood that something is used to sort the solutions. So the sorting is done based on the ranking that I have just discussed how to calculate. So let's say one is ranking 1, one is ranking 2, one is ranking 3, and one is ranking 4. It can be anything. And this is the 2n solutions. Out of this, you select the top n solutions for your new generation. And as it was discussed that these things will have same rank. So how do we select among them? So for that, the crowding distance is used. So solution with same rank are judged based on crowding distance. So let's say if you have these many solutions, and it is directly proportional, so the fitness value will actually become directly proportional to crowding distance. So if it is well separated from the previous and the succeeding point, then it will be selected. How it is calculated crowding distance? It is the perimeter of rectangle made by the adjacent solutions in objective function space. So this is f1, f2, and this is your solution fi. You want to calculate, sorry, this is your f1 dash, f2 dash. You want to calculate the crowding distance, you get the perimeter of this rectangle. That will be the crowding distance. So when you have solutions of the same rank, then you use the solutions with more crowding distance, because what do you want to do at the end of the day? You want a very good spread of objective functions in the objective function space. So that's why you will select a solution that is well spread out rather than a solution which is like here. So this one will be selected. Okay, now that we have discussed the basic concepts of the, so one thing to remember, it is elitism. So I think the spelling of elitism is not starting with I, it starts with E. So ELI, elitism approach, uh, because getting Pareto optimal front, because the initial population also participates in the selection algorithm. Okay. So that's that. We have discussed the concepts of all the possible methods, or all the very common methods that are used for multiple objective optimization. I apologize for my handwriting. So now what we will do is we will start coding. What we will do is we will code we will code one function. We'll code the same function in one NSGA2 in R, and the same problem we'll do it in Moga in MATLAB. Okay, so let's start. I will write the problem here. It is the same as search problem. Okay, so the question is, you have to do the minimization of f1, f2, f3. These are the objective functions. They go like this. So we have 0.5 x1 square plus x2 square plus sine of x1 square plus x2 square. This is first objective function. Second objective function is 3 x1 minus 2 x2 plus 4 power 2, that is square, divided by 8, plus uh, x1 minus x2 plus 1 square divided by 27 plus 15. And f3 is written as 1 by x1 square plus x2 square plus 1 minus 1.1 exponential of minus x. Okay, so this is actually minus of whole x1 square plus x2 square. So these are the three objective functions, and we are going to do perform the optimization with no constraint and all. We have already seen how to apply. So the same way you can apply the constraints here also. And the lower limit of, so it is a two variable function, x1 and x2. Lower limit for x1 is minus 3, and lower limit for x2 is minus 3. Upper limit is 3, upper limit is 3. This is kind of the solution space. Now let's write the code that does this optimization. So let me share my screen. Okay, so when we do allow, so we are sharing our screen and we will open R. You can see I have already practiced how to do these things. We'll just code together, and we will see what we can get. Let me just leave the meeting from my tab. The call, just leave the call. Okay. Now let's. I hope I am audible. Let me check once. Let me stop this and let me start from. Okay. So I hope my screen is visible. So since none of you are here, I cannot know whether my voice is getting recorded or not. Let's hope it is. Let me just see the screen also. Okay. And let's solve these problems quickly. Okay. So we have to import the library for NSGA2R, library NSGA2R. And since I want to plot scatter in 3D, I need to import the library or plot 3D also. Okay, so we will define the objective functions. So we have OB, let's name it OBJ, oh yeah, fun is equal to function that takes x as a vector, sorry, x is a vector, and this is the content inside the function. We have our first function, that is f1, first objective function 0.5 into inside brackets x square bracket 1 square plus x square bracket 2 square and plus sign. Inside that also we have x1 square plus x2 square. This is the first f2. Second objective, we had 3x1, okay, nothing, then x2 minus of x minus of 2x2 and plus 4 square of the whole thing, then the whole thing divided by 8. So what you can do is you can give bracket here also, so that it is not confusing that it's the power of 2 by 8, it's square and then the whole thing is divided by 8. Good practice to do, so that in exam when we are in hurry we don't make any kind of silly mistakes. x2 plus 1 square divided by 27 plus 15. What we can do is we can go here and give a bracket here. So this is f2. I hope the error should go away. It seems the error is not going. Okay, because we have not given the vector. Let me see what is going on here. It is somehow getting into this. That is fine. And oh, here I have missed the multiply sign. Okay, now it is clear. F3, and then it is 1 by x 1 square plus x 2 square plus 1 minus 1.1 into exponential of minus of x 1 square plus x 2 square. So that's it. We are returning a function here, and that function, so what sir used was something called r bind, that is combining the function values using in the row. So the same thing can be done using the C that we use normally. So let's not make it complicated and let's use C itself. So this is the function, and this is getting a return. So let's do return function. Let's give it under bracket. I think it wants it under bracket. Yeah, so let's return the. We can do this also. We can just replace this here and now talk about that. Yeah, that's what we can do. And let's write the code for the NSGA, non-dominated sorting genetic algorithm. So we have NSGA2. So one interesting thing about this is while importing, you import NSGA2R, but while using you do NSGA2. So I was having a problem when I was actually practicing myself. And so this thing you should keep in mind. I was giving NSGA to R and it was showing some other error. So we have to use NSGA2. So first is the objective function. Second is the number of variables, then number of objective functions, and generations. Then we have to give generations. Let's say we give 100 in the start, and we give pop size. Let's say we give 100 that also, and lower dot bounds. So something different here. Previously, what we were looking at was we can just give lower, and we didn't need to give the structure in the field inside the structure. But this time we have to give. So the lower bound of x1 is -3, x2 is also -3, and then the upper bound, sorry, upper dot bounds. Sorry, we have c combination of 3 and 3, and yeah, that is it. That is the minimum requirement to run this. And now let's just save it. Control S, Control A, Control Enter. Then you have solved the result. It is being stored in the result. Let's just see what are all the things in result. Just plot, just type result and enter, and you will see that you have optimal class in result, and you have something called function values, which are unfortunately becoming NaN. So fortunately, we are getting the function values also as NaN. So that means I have done some mistake in writing this code. Let me just look at it. So it is good that we make mistakes so that you also know that what kind of mistakes can be made here. So let us see if I remove these brackets that I was using, do we get any different solution. Let's control A, shift, control enter, and then we just put res true and NaN. So that's not the thing. So we did correct only at that point. Most probably, if my guess is correct, we have a problem somewhere here. So let's look at it a little bit more carefully. Okay, what what if I use R bind? I don't think this should be the problem. Let's keep here rs c. Okay, rs values. Let's see what we are getting here. Control A, Control A, Control Enter. We are getting NaN. Again, lower bound is -3, -3. Is it because of the name? I am not very sure. Let us give objective function, and maybe that thing is assigned to someone, and that is creating kind of a problem. Nope. So that is also not the case. So if you are able to spot the problem, then maybe you can move forward to the point where we are discussing the other question or the MATLAB, same code in MATLAB. I'm not able to find any problem here. Usually when NaN is appearing in your solution, the problem is somewhere in your this function where denominator is something, that you are using, and seem to be doing fine when. So let me just do this. Let me open the. I don't want to waste any more time. Let me open the code that I had written earlier and just compare what is the problem here. So if you look at it, let's run this code and let's see. This is the corrupted one. This relay. Enter, and you get a function. What might be the problem with this? Let me get the objective functions and if you think it is time waste, then please feel free to move forward. But this kind of problems can happen to anyone at any time, and to know what kind of mistake, silly mistake, or else any other kind we are making, it is important. So, hmm, we have the same F1, we have the same F2, we have the same F3, and we have the same F3. We have the same F3. What we can do is we can use this, or we can comment this and run this and see if the problem was. So the problem is not in the optimization optimization problems or the optimization equations. The problem is somewhere here. So did I give the spelling of generation wrong? Maybe I have done that. Generations delete population size is pop size, lower dot bounds we have, upper dot bounds we have, and so I'm not sure what is going on here, but you see that this is working. So if you are able to figure out what is the problem with this, feel free to correct it. And so this is how you do you the results. The result or the value of the objective functions is stored in result dollar values, and you can see them. So this is the F1, this is the F2, F3, and this is kind of a Pareto front. And yeah, these are not the actual. Let me just control L it and re, rewrite it again here. Okay, these are the values F1, F2, F3, and based on these values, you will see what is the value of F1, F2 that you want to give to you want to have. What is the value of F2 you want to have in your particular scenario? That requires the field study and all those things. So that is not in the syllabus. Okay, so we have done the same the problem in NSGA, non-dominant sorting genetic algorithm. Let's copy this because the equation we are going to use same. Let's copy this equation and do the same thing in using multi-objective genetic algorithm in MATLAB. So first of all, CLC and clear variables, close all. Okay, now let's make the function. So in this, what we do is we have x square bracket 1. So we do control C is copy and control F. And we since in MATLAB we use curly brackets, so we are not curly, normal brackets. So we are going to replace x square 1 with x normal bracket 1, and we'll replace all. So that is gone, error. That error is gone. Same thing we are going to do with x square bracket 2 also, and replace all. So that's gone. Now the here's we don't need return. We need to just give value as the function is equal to f1 colon f2 colon f3. You can do colon or comma. You do colon, that means it is going to store in row 1, row 2, row 3. You do comma, it is going to store in column 1, column 2, column 3 of the first row, and we need to give here semicolon so that it doesn't print the value every time. Okay, so this is a function that we have to define. Let's give the comment here. And how we define function in MATLAB is function, then space output is equal to function name and input. So let's call it func. Here F3 is not used, it is telling, because I repeated F2 here, so I need to keep F3, and we can remove this curly bracket and put end. Now this is the proper definition of a function, and in MATLAB we need to have the uh, function definition in the end of the script. So this is going to be in the end, and above we are going to define our problem. So lower bound is equal to -3 comma -3, upper bound is equal to 3 comma 3, and what do we have? Objective function. We have objective function as, what is the name we have given? We have given the name func, right? So it will be at the rate func. And now see in R, what we saw was we could increase the population size inside this itself. Previously we have done control arguments for R, but in that we have increased the CF for different values such as particle sorting optimization and differential evolution. But here we could directly give population size. But in case of MATLAB, just a little bit of a problem, that not a problem, let's say extra work that we have to do is we have to define something called options, that is going to be associated with an optimization function, and it is optimization options. It is going to be associated with what we are going to use here, GA multi objective, and here you need to give your population size of, let's say we give 500 or 500. Okay, so this is our options, and we are going to use these options in our uh, when we defining or calculating the multi-objective genetic algorithm. How do we call it? GA multi OBJ, and we give it the objective function, and we give it the number of variables, that is 2. Are there any kind of inequality or linear constraints, either of inequality or of equality? We don't have them, so they are empty. Is there any lower bound, upper bound? Yes, we have lower bound and we have upper bound also, so that we keep here. And do we have any some specific things that we are trying to change in this optimization algorithm? That is, we have defined in options, so we give options. So we calculate this, and optimization has terminated. Average change of spread of Pareto solution has reached less than the tolerance. Okay, so now let's see what do we have. So we want to plot the Pareto front. That means we want to plot a line in the solution objective function space. So it will be stored in FL. Let's see what is there in FL. We have 3 columns. So we can use scatter 3 in MATLAB. No need to import anything. FL, and when you want to select a column, a whole column, the whole all the rows of column number 1. So you do all the rows is colon and comma 1, and same thing for column number 2, all the rows of column 2, column number 3, all the rows of column 3, and then you can actually give the size of the scatter plot. I like to give, let's say, 20, and you can give the color, whether it is hollow or filled. So color is R and it is filled. So just save it and run it. We have a Pareto front, and it is very nice in MATLAB that we can rotate also, and you can also give X label, that is F1 and Y label and Z label are 2 and F3. So y label is 2 and z label is 3, so that you know which axis corresponds to which. So F2, F1, F2, F3. So this is your Pareto optimal front, and then you go in this thing and see which what is the significance or importance you want to give to each F1, F2, F3, and get the value of x1, x2 to get that particular Pareto point in Pareto front. Okay, so this is it that I wanted to discuss in today's session. All these things, why I didn't discuss, if you uh, forget or you not watching the starting of the video, is because all the other topics we have already done in R. So just changing the syntax and doing it in MATLAB doesn't make much of a sense. You can just copy paste the equation, and you will also get some practice if you are converting a code from one language to another. You'll get opportunity to learn both the languages. Okay, so that's all for the last session for optimization methods for civil engineering. I hope I was able to increase at least 1%, or able to contribute at least 1% to in your knowledge, and all the best for your exams. Thank you. So I'll end the session now.